We have all stared at this screen. Just a moment. cetus.turing.ac.uk. Below that, a brief note that the system is performing security verification. Technically, this is a Web Application Firewall, or WAF, challenge interstitial. This delay is the product of an active security gate, rather than server latency or a passive loading state. The system is conducting a forced, multi-layered computational interrogation of the local machine. While the browser spins, an invisible architecture is executing cryptographic handshakes, testing your computer's local execution environment, and tracing your request against a global database. The simplistic user interface deliberately masks a zero-trust architecture designed to forcefully filter incoming internet traffic in real time. This diagram models the TCP connection between client and edge server. They execute a TLS handshake, exchanging keys to encrypt the pipeline. The browser checks the SSL certificate, verifying the server. But crucially, this process performs absolutely zero verification on the nature of the client. Automated, malicious scripts are perfectly capable of executing valid TLS handshakes. Without further checks, establishing a secure connection simply provides a protected tunnel for bots to execute attacks against the application. Cryptographic security ensures data is safe while moving across the network, but it cannot prove if the sender is a human or an automated script. This brings us to the next line on the challenge screen. This website uses a security service to protect against malicious bots. These bots perform Layer 7, or application layer attacks. Instead of targeting credential stuffing, where scripts rapidly test stolen passwords, or massive botnets scraping data until server resources are completely exhausted, the server faces a dilemma. An HTTP request from a real browser looks identical to an HTTP request from a malicious Python script. The solution is a proof-of-work requirement. The server forces the client to spend its local computational resources to prove its legitimacy. The economics of operating a botnet rely on extreme efficiency. Attackers use the lightest possible scripts to maximize output. Forcing those scripts to perform heavy computations destroys their return on investment. To scale defense against automated threats, web architecture must shift from passively reading incoming requests to actively demanding computational friction that cheap bots cannot afford. We see this computational friction in the instruction, "Enable JavaScript and cookies to continue." A headless bot is a lightweight script built on tools like curl, designed to parse raw HTML text without ever rendering a visual user interface. To remain fast and resource efficient, these headless bots intentionally strip out complex components, including JavaScript runtime engines. The server transmits an obfuscated JavaScript workload to the client. The browser executes this code to verify internal APIs and generate a mathematical hash. Lacking a JavaScript engine, the headless script cannot execute the verification logic. It fails, and its connection is dropped. Once the computational proof is generated, it must be stored for future requests. When the server receives the correct answer to the JavaScript challenge, it issues a session clearance cookie. This cookie acts as a persistent passport, allowing the user to browse the site subsequently without being interrogated on every single page load. JavaScript and cookies function as technical evidence that a full, resource-heavy execution environment is present on the client device. At the bottom of the challenge screen is a long alphanumeric string, Ray ID 9EF4F108AC2E35AC. The Ray ID is a unique, cryptographically generated identifier assigned exclusively to this single web request at the edge server. This map shows the scale. This specific request is one of millions happening simultaneously across a global edge network. Under this Ray ID, the server collects precise telemetry, originating IP, TLS cipher, and challenge pass-fail status. This localized telemetry is instantly broadcast globally. If a botnet fails a challenge in one geographic region, its IP signature is immediately blacklisted globally across all servers sharing that threat intelligence. The Ray ID turns an isolated network request into an actionable data point, continuously training and hardening the global security perimeter in real time. Finally, the screen updates. Verification successful. Waiting for cetus.turing.ac.uk to respond. What you experience as a 3-second delay actually encompasses a TLS handshake, a localized environmental puzzle, and a global telemetry update. By relying on background JavaScript challenges, this automated methodology significantly reduces user friction compared to older security methods that required manual CAPTCHA image selection. The reality of modern web hosting is that default public access is no longer viable. All incoming traffic must be treated as hostile until it is computationally proven otherwise. These invisible, relentless interrogations are the foundational mechanisms allowing the modern web to remain openly accessible while surviving constant automated siege.